Okay, welcome to another video in the Wild Networking series. I dropped the sport coat pretty darn quick. I kept it for a while, but my main focus is just getting through all this material and having this series be more about that than whether or not I'm wearing a sport coat. But I do apologize for anyone who was specifically watching this series for that. You can go back and watch the earlier videos if that is what drew you to this series. But before I get started with anything else, I would like to give a huge shout out to this channel here, because a lot of what you see in the real world for network engineering, in my opinion, is going to be more like CCNA, maybe beginning CCNP level stuff. Like most of what's out there is covered in lower level networking courses. The edge cases, the really difficult technical stuff you see on the CCIE, JNCIE, really not going to encounter as much. So if you're like me, where you're going for your E-level exams and you took your A-level exams 5 years ago and you're kind of struggling to, like, when you hear the word ARP scaling, you don't even know what that means until you start reading it and you're like, oh, is this just talking about making sure that those ARP broadcasts aren't encompassing too much network traffic? And you realize, oh yeah, it is. Okay, yeah, I learned that 5 years ago. I'm very comfortable with that. You can watch this channel here, this Looking Point Inc. Great channel, short videos, and they really give a good explanation of the basics, no fluff, all right on topic and relevant, unlike this channel. But I will continue where I left off last, which was section 5, layer 2 practices to scale ARP/ND. And this will be hopefully the final video on ARP scaling. It's going to be hard cut at an hour, as well as the last video was. Practices to alleviate NPR? APR? What's APR? Okay, well, I guess this is a typo. I think they mean ARP, because there's no explanation about, like, APR. Isn't that like something, isn't that like a finance term? But I'm pretty sure they mean ARP here. Okay, so these are practices to alleviate. I can't help but see that as APR, because it says APR. The thing they're talking about, burden on L2/L3 boundary routers. The ARP/ND broadcast/multicast messages in a layer 2 domain can negatively affect the L2/L3 boundary routers, especially with a large number of VMs and subnets. This section describes some commonly used practices for reducing the ARP/ND processing required on L2/L3 boundary routers. It's just this kind of, I find this funny because they're using this term so many times. I don't understand how they can have a typo on it when it's like, how does this not jump out? But anyways, moving on. Communicating with a peer in a different subnet. So, okay. So I'm going to read this again because this really distracted me way too more than it. There, I'm gonna put it on the. There we go. It's gone now. The ARP/ND broadcast/multicast messages in a layer 2 domain can negatively affect the L2/L3 boundary routers, especially with a large number of VMs and subnets. This section describes some commonly used practices for reducing the ARP/ND processing required on the L2/L3 boundary routers. So this is a key one here, the L2/3 boundary routers. This is what we discussed in the last video, where you can make a decision whether you want those routers on your edge or whether you want those routers just on your uplinks, your edge uplinks, the devices that your edge layer. And oops, my video stopped. Let me restart that. Looks like I can't restart that. So I don't know what. Oh, okay, here we go. Perfect. Okay, so I was talking about the L2/L3 boundary routers and the fact that you can make a design choice on where you want those routers to be. You can design it so that those routers are on the network edge, as we see here, or you can design it so that those routers are beyond the network edge, as we can see here. So there are trade-offs to each design. The only real trade-off in the layer 3 access design is that you won't be able to handle a specific edge cases. So really there's no reason to ever design the network without layer 3 extended to the access. So without your L2, L3 boundary routers being the access routers, unless you have a special case that does not allow for that, where for some reason you have like special traffic or something that can't be routed and just requires a broadcast domain. Yeah. So, but even in that case, you can have, if you've got multi-layer switches down here, you can have your L2, L3 boundary on the edge, but you can give a special VLAN to that one, and you can extend that VLAN up to the layer 3 and just have one VLAN go through your network in a single broadcast domain while still extending layer 3 down for your other devices, because you can cut it up like a piece of cake port by port and give special cases to special ports. So the reason you want layer 3 access to be the preferred design and then make special cases for layer 2 is because you have to have one of these links blocked in order to prevent spanning tree loops when it's layer 2. You don't need that when it's layer 3 because you'll be exchanging routes, and you can use all the links and you can have redundancy. But here you've got to have one link turned off, or else there's going to be broadcast storms from the ARP broadcast traffic. So ARP won't scale as well in this topology because ARP is going to be traversing through all of these links. Here you just have point-to-point ARPs for the IP addresses, and then you're exchanging IP routes, and you have routing protocols to do that, dynamic routing protocols. So like this router here will be learning about this link through a dynamic routing protocol instead of just broadcasting traffic out through that link and having it come back to it in a loop, unless one of these links were taken down. So you get more bandwidth, you get more control over the direction your traffic goes on the network, and you get easier configurability because you can set up those. You can work with routing tables and routing protocols instead of spanning tree, which has recalculation times. So it takes like 45 minutes for it to go to like listening, learning, forwarding. So in that time, it might cut off your legs when you're in in-band, and it's just much better to work with layer 3. So when it comes to ARP scaling, you want to, basically the best way to scale ARPs is to build your L2, L3 boundary at the access layer. And if you need a special case for a special device, you can do that in a special way. by using a special VLAN. Alright, section 5.1.1.1, communicating with a peer in a different subnet scenario when the originating end station doesn't have its default gateway MAC address in its ARP/ND cache and needs to communicate with a peer in a different subnet. It needs to send ARP/ND request to its default gateway router to resolve the router's MAC address. If there are many subnets on the gateway router and a large number of end stations in those subnets that don't have the gateway MAC address in their ARP/ND caches, the gateway router has to process a very large number of ARP/ND requests. This is often CPU intensive, as ARP/ND messages are usually processed by the CPU and not in hardware. So one of the overarching questions I'm going to be answering in this series here, and I'll pull up a WordPad and list that question here, and then I'll put this question in the notes, is why is my internet so slow? So if we ever get this question, so this is a question you'll hear in the wild a lot. A lot of people complain about their internet being slow. You're the network engineer, you've got to have an answer to this. So as we go through all of this, we'll be giving answers. One thing I want to give from the last video is the answer that so MAC Table Exhaustion. So if there's more MAC addresses being learned on a switch than the table has capacity for, the switch turns into a hub and it just broadcasts all traffic out, and then you've got that's ARP scaling issues. It doesn't scale that way properly, so you have most of your bandwidth going towards these ARP broadcast messages, and your internet slows down that way. So if your devices are learning more MACs than they are capable of, then your internet will all of a sudden suddenly go slow. And that's one of those things where you're on the internet, everything's working fine, and then all of a sudden it just stops. Well, what the heck happened? It could be MAC table exhaustion. All of a sudden, like a new user plugged in, or like a new port was turned up, and now the switch is learning an extra MAC, and that's one more MAC than the switch had capacity for. So now it's broadcasting all of the ARPs out all of the ports and hogging the bandwidth for those ARP broadcast messages, and leaving you with very little for what you actually need to do. So that's the first answer. Another answer could be spanning tree recalculation. So let's say that there's some a link went down, and you don't have your layer 3 layer 2 layer 3 boundary routers and your access layer, and you've got a link blocked by spanning tree, and then another link goes down. Well, it's got to unblock that link, it's got to make new recalculations, so it's going to take the traffic down, make it slow for about a full minute. So that's another good answer to the question, why is my internet so slow? Because there was a failure in the links, and spanning tree needed to make a recalculation. Okay, so let's keep going with this. Note any centralized configuration that preloads the default MAC address is not included in this scenario. Solution. For IPv4 networks, a practice to alleviate this problem is to have the L2/L3 boundary router send periodic gratuitous ARP messages so that all the connected end stations can refresh their ARP caches. As a result, most, if not all, end stations will not need to send ARP requests for the gateway routers when they need to communicate with external peers. For the above scenario, IPv6 end stations are still required to send unicast ND messages to their default gateway router, even with those routers periodically sending unsolicited neighbor advertisements, because IPv6 requires bidirectional path validation. Okay, I actually didn't know this, so I'm going to take a note here. Advantage: this practice results in a reduction of ARP requests to be processed by the L2/L3 boundary router for IPv4. This practice, what was the practice again? To have, okay, gratuitous ARPs. Disadvantage: this practice doesn't reduce ND processing on the L2/L3 boundary router for IPv6 practice, for IPv6 traffic. So the practice is to have gratuitous ARPs sent out on your L2/L3 boundary routers, whether those be at the distribution or access layer. Recommendation: if the network is an IPv4 only network, then this approach can be used. For an IPv6 network, one needs to consider the work described in RFC 7048. Note ND and Secure Neighbor Discovery, SEND. What does the E stand for? Oh, probably secure. RFC 3941, use the bidirectional nature of queries to detect and prevent security attacks. L2/L3 boundary router processing of inbound traffic. Scenario: when an L2/L3 boundary router receives a data frame destined for a local subnet and the destination is not in the router's ARP/ND cache, some routers hold the packet and trigger an ARP/ND request to resolve the L2 address. The router may need to send multiple ARP/ND requests until either a timeout is reached or an ARP/ND reply is received before forwarding the data packets towards the target's MAC address. This process is not only CPU intensive but also buffer intensive. Solution: to protect a router from being overburdened by resolving target MAC addresses, one solution is for the router to limit the rate of resolving target MAC addresses for inbound traffic whose target is not in the router's ARP/ND cache. When the rate is exceeded, the incoming traffic whose target is not in the ARP/ND cache is dropped. For an IPv4 network, another common practice to alleviate pain caused by this problem is for the router to snoop ARP messages between other hosts so that its ARP cache can be refreshed with active addresses in the L2 domain. As a result, there is an increased likelihood of the router's ARP cache having the IP-MAC entry when it receives data frames from external peers. RFC 6820, section 7.1 provides a full description of this problem. I'm not following. Neighbor unreachability detection is too impatient. Secure neighbor discovery. Arp processing on routers. Oh, okay. Yeah, this looks like it could be useful. Advantage: this practice results in a reduction of the number of ARP requests that routers have to send upon receiving IPv4 packets and the number of IPv4 data frames from external peers that routers have to hold due to targets not being in the ARP cache. Disadvantage: the amount of ND processing on routers for IPv6 traffic is not reduced. IPv4 routers still need to hold data packets from external peers and trigger ARP requests if the targets of the data packets either don't exist or are not very active. In this case, IPv4 processing or IPv4 buffers are not reduced. Recommendation: if there is a higher chance of routers receiving data packets that are destined for non-existent or inactive targets, alternative approaches should be considered. Okay, next section, inter-subnet communications. The router could be hit with ARP/ND requests twice when the originating and destination stations are in different subnets attached to the same router and whose hosts don't communicate with external peers often enough. The first hit is when the originating station in subnet A initiates an ARP/ND request to the L2/L3 boundary router if the router's MAC is not in the host's cache. And the second hit is when the L2/L3 boundary router initiates ARP/ND requests to the target in subnet B if the target is not in the router's ARP/ND cache. Again, practices described in sections 5.1.1 and 5.1.2 can alleviate some problems in the IPv4 networks. For IPv6 traffic, the practices described above don't reduce the ND processing on L2/L3 boundary routers. Recommendation: consider the recommended approaches described in sections 5.1.1 and 5.1.2. However, any solutions that relax the bidirectional requirement of IPv6 ND disable the security that the two-way ND communication exchange provides. Okay, so now this is static ARP/ND entries on switches in a data center environment. The placement of L2 and L3 addressing may be orchestrated by server or VM management systems. Therefore, it may be possible for static ARP/ND entries to be configured on routers and or servers. Advantage: this methodology has been used to reduce ARP/ND fluctuations in large-scale data center networks. Disadvantage: when some VMs are added, deleted, or moved, many switches' static entries need to be updated. In a data center with virtualized servers, those events can happen frequently. For example, for an event of one VM being added to one server, if the subnet of this VM spans 15 access switches, all of them need to be updated. Network management mechanisms, SNMP, the Network Configuration Protocol, netconf, or proprietary mechanisms, are available to provide updates or incremental updates. However, there is no well-defined approach for switches to synchronize their content with the management system for efficient incremental updates. Recommendation: additional work may be needed within IETF working groups. For example, netconf, NVO3, those things, to get prompt incremental updates of static ARP/ND entries when changes occur. Alright, so there's also the ARP/ND proxy approaches. RFC 1027 specifies one ARP proxy approach referred to as Proxy Arp. However, RFC 1027 does not discuss a scaling mechanism. Since the publication of RFC 127 in 1987, many variants of Proxy Arp have been deployed. RFC 1027's Proxy Arp technique allows a gateway to return its own MAC address on behalf of the target station. ARP reduction describes a type of ARP proxy that allows a Tor switch to snoop ARP requests and return the target station's MAC if the top of rack has the information in its cache. However, RFC 4903 doesn't recommend the caching approach described in ARP reduction because such a cache prevents any type of fast mobility between layer 2 ports and breaks secure neighbor discovery. IPv6 ND proxy, RFC 4389, specifies a proxy used between an Ethernet segment and other segments, such as wireless or PPP segments. ND proxy, RFC 4389, doesn't allow a proxy to send NA messages on behalf of the target to ensure that the proxy does not interfere with hosts moving from one segment to another. Therefore, the ND proxy RFC 4389 doesn't reduce the number of ND messages to an IP to an L2/L3 boundary router. Bottom line, the term ARP/ND proxy has different interpretations depending on vendors and/or environments. Recommendation for IPv4, even though those proxy ARP variants, not RFC 1076, have been used to reduce ARP traffic variations in various environments, there are many issues with scaling. The IETF should consider making proxy recommendations for data center environments as a transition issue to help DC data center operators transitioning to IPv6. Section 7 of the RFC 4389 Guidelines to Proxy Developers should be considered when developing any new proxy protocols to scale ARP. Okay, 5.4, multicast scaling issues. Multicast snooping, IGMP/MLD, I guess I'm not sure what that is, has different implementations and scaling issues. RFC 4541 notes that multicast IGMP v2/v3 snooping has trouble with subnets that include IGMP v2 and IGMP v3. RFC 4541 also notes that MLD v2 snooping requires the use of either destination MAC, DMAC address filtering, or deeper inspection of frames/packets to allow for scaling. MLD2 snooping needs to be re-examined for scaling within the DC data center. Efforts such as IGMP/MLD explicit tracking for downstream hosts need to provide better scaling than IGMP/MLD v2 snooping. Practices to scale ARP/ND in overlay models. There are several documents on using overlay networks to scale large layer 2 networks or avoid the need for large L2 networks and enable mobility. L3 VM mobility VXLAN. VXLAN is familiar to me. Transparent interconnection of lots of links, trill, and IEEE 802.1AH, Mac in Mac. Oh man. are other types of overlay networks that can scale layer 2. Overlay networks hide the VM's addresses from the interior switches and routers, thereby greatly reducing the number of addresses exposed to the interior switches and router. The overlay edge nodes that perform the network address encapsulation / de-encapsulation still handle all remote stations addresses that communicate with the locally attached end stations. For a large data center with many applications, these applications' IP addresses need to be reachable by external peers. Therefore, the overlay network may have a bottleneck at the gateway nodes in processing resolving target stations' physical addresses, MAC or IP, and the overlay edge addresses within the data center. Here are two approaches that can be used to minimize this problem. Use static mapping as described in section 5.2. Have multiple L2/L3 boundary routers, i.e. routers, with each handling a subset of stations addresses that are visible to external peers. For example, gateway number 1 handles a set of prefixes, gateway number 2 handles another set of prefixes, etc. Summary and recommendations. This memo describes some common practices that can alleviate the impact of address resolution on L2/L3 gateway routers. So let's think about what those were. So one of them was Gratuitous Arps. So let's see here. Alleviating impact of address resolution on L2/L3 gateway routers. So one of them I remember was Gratuitous Arps. Okay, so that way you're not relying on so when you send out Gratuitous Arps, then you, at a regular interval, you're setting out one ARP to make sure that all your tables are up to date, instead of having all those places that aren't up to date have their tables expire, and then they all send out an ARP to try to get things right. So you can have, you know, the captain of the football team, you know, tell people something, or you can have all the people tell the captain something, and the captain gets overwhelmed. Although that's a really bad analogy, because the captain would probably get overwhelmed telling a bunch of people things, but I don't think it's the worst analogy in the world. So Gratuitous ARPs are one way. Another way is static MAC tables, and you can automatically update via netconf or some other thing. So if you're going to, so you make sure that you're not relying on broadcast traffic. You're relying on a unicast tool, or a tool that uses unicast traffic, and you update your MAC addresses that way. The other way, yeah, so that's static. Where's the ARPs? I don't see it. Okay, so that's another thing you can do, is you can use like a policer. So policer to rate limit ARPs and drop extra ARP traffic that would otherwise overwhelm the device. Yeah, so here's the gratuitous ARPs. Yeah. Ah, this is the static. I have that listed there. And it would be static ARP tables. Yeah, you can also use you can also use ARP proxy variants, proxy ARP variants. I don't know that much about that though. And it doesn't work for IPv6. Okay, so that's the 5F guide. You can have gratuitous ARPs go out from your boundary routers. You can have static ARP tables instead of relying on those automatic update broadcast messages. You can have a policer limit ARPs, so you're just dropping extra ARP traffic instead of exhausting your MAC table capacity and turning your switches into hubs. Or you can set up proxy ARP, which is not effective for IPv6 and not scalable and really not the best solution, but it is something that you can look into in a special case that calls for it. What that special case is, I don't know, but if gratuitous ARPs, static ARP tables, and policing ARPs are not solving your problem, you can do a deeper dive into proxy ARP. In some of these scenarios, the common practices could be improved by creating or extending existing IETF protocols. These protocol change recommendations are relax the bidirectional requirements of IPv6 neighbor discovery in some environments. However, other issues will be introduced when the bidirectional requirement of neighbor discovery is relaxed. Therefore, it is necessary to have performed a comprehensive study of possible issues prior to making those changes. Create an incremental update scheme for efficient static ARP ND entries. Develop IPv4 ARP/IPv6 ND proxy standards for use in the data center. Section 7 of the RFC 4389 Guidelines to Proxy Developers should be considered when developing any new proxy protocols to scale ARP/ND. Consider scaling issues with IGMP/MLD Snooping to determine whether or not new alternatives can provide better scaling. Security considerations. This memo documents existing solutions and proposes additional work that could be initiated to extend various IETF protocols to better scale ARP/ND for the data center environment. Security is a major issue for data center environments. Therefore, security should be seriously considered when developing any future protocol extensions. Okay. Alright, so I got through it. I'm only at the 40-minute mark, so there was another one that depended on this a bit. Now, unfortunately, I don't think this was that useful. I mean, this is a lot of depth, but I'm just not sure if it's relevant depth. I think depth is obviously important, but relevant depth is more important in my opinion. Let's see here. So that's what I'm looking for, is relevant depth. So I think to get that, I'm gonna go and find one of the, yeah, so here's a related RFC that describes the, so I think this is how I can get more relevant depth, by looking into this one next. Yeah, this looks perfect. Yeah. Oh, this is really good. Okay, so this is going to be the next one. We're going to try to get through as much of this as I can now, but this will be the focus of the next video as well, I think. But this is address resolution problems in large data center networks. Abstract. This document examines address resolution issues related to the scaling of data centers with a very large number of hosts. The scope of this document is relatively narrow and focuses on address resolution, the address resolution protocol ARP, in IPv4 and neighbor discovery in IPv6 within a data center. Status of this memo: this document is not an Internet Standards Track specification. That's interesting. It is published for informational purposes. Well, can I see I think I've tried to oh, here we go. So here's the official Internet Protocol standards. So is there one for ARP? Oh, here we go. So here's the one for ARP, RFC 826. Now these are really old, 1982. So I don't know how relevant that is. Oh, here's the there's 129. Okay, there's only 9. So address resolution for instant messaging and presence. Fiber channel. Okay, so that might be worth it to look out for, but this is interesting here because it looks like this page contains the current lists of Internet standards, draft standards, and proposed standards. But I'd like to just narrow it down to, okay, here, yeah. So it does narrow it down to just the Internet standards, yeah. So this is kind of the core of established network engineering here, because these are all the Internet standards for, oh, no, well, no, these are the draft standards, but these are all of the actual internet standards here. I wish I knew what the difference was between an internet standard and a draft standard. I'm pretty sure it'll tell me. Okay, so the internet, a loosely organized international collaboration of autonomous interconnected networks, supports host-to-host communication through voluntary adherence to open standards and procedures defined by internet standards. There are also many isolated interconnected networks which are not connected to the global internet but use the internet standards. The internet standards process described in this document is concerned with all protocols, procedures, and conventions that are used in or by the internet, whether or not they are part of the TCP/IP protocol suite. In the case of protocols developed and or standardized by non-internet organizations, however, the internet standards process normally applies to the application of the protocol or procedure in the internet context, not to the specification of the protocol itself. In general, an internet standard is a specification that is stable and well understood, is technically competent, has multiple independent and interoperable implementations with substantial operational experience, enjoys significant public support, and is recognizably useful in some or all parts of the internet. Cool. All right. But this is not that. This is an informational RFC. It's not an internet standard. I wonder if there's informational ones. What's an informational RFC? Okay, so that sucks. Like, it looks like the distinction between a informational and a standard track RFC or internet standard is like really loose. Like, basically when they meant to have it be a standard, sometimes they'll have it be informational. Like DNS looks like it's informational. And it's and it's just not a standard. Yeah, so there's 3,000 matches for proposed standard on this page. Only 114 for an internet standard. It's, I guess, not so bad. Okay. This document is a product of the Internet Engineering Task Force. Okay. Alright, let's start with the introduction here. This document examines issues related to the scaling of large data centers. Specifically, the document focuses on address resolution, ARP in IPv4, and neighbor discovery in IPv6 within the data center. Although strictly speaking, the scope of address resolution is confined to a single L2 broadcast domain. For example, ARP runs at the L2 layer below IP. The issue is complicated by routers having many interfaces on which address resolution must be performed, or with the presence of IEEE 802.1q domains, where individual VLANs effectively form their own L2 broadcast domains. Thus, the scope of address resolution spans both the L2 link and the devices attached to those links. This document identifies potential issues associated with address resolution in data centers with a large number of hosts. The scope of this document is intentionally relatively narrow, as it mirrors the address resolution for massive numbers of hosts in the data center ARMDWG charter. This document lists pain points that are being experienced in current data centers. The goal of this document is to focus on address resolution issues and not other broader issues that might arise in data centers. Terminology. Address resolution. The process of determining the link layer address corresponding to a given IP address. In IPv4, address resolution is performed by ARP, RFC 0826. In IPv6, it is performed by neighbor discovery, ND, RFC 4861. Application, software that runs on either a physical or virtual machine providing a service, for example, web server, database server, etc. L2 broadcast domain, the set of all links, repeaters, and switches that are traversed to reach all nodes that are members of a given L2 broadcast domain. In IEEE 802.1q networks, a broadcast domain corresponds to a single VLAN, host or server, a computer system on the network, hypervisor, software running on a host that allows multiple VMs to run on the same host, virtual machine, VM, a software implementation of a physical machine that runs programs as if they were executing on a physical non-virtualized machine. Applications generally do not know they are running on a VM as opposed to running on a bare host or server, although some systems provide a para-virtualization environment that allows an operating system or application to be aware of the presence of virtualization for optimization purposes. TOR, top of rack switch, a switch placed in a single rack to aggregate network connectivity to and from hosts in that rack. EOR, end of row switch, a switch used to aggregate network connectivity from multiple racks. EOR switches are the next level of switching above TOR switches. Oh my god. Okay, so the background. A large flat L2 networks have long been known to have scaling problems. As the size of an L2 broadcast domain increases, the level of broadcast traffic from protocols like ARP increases. Large amounts of broadcast traffic pose a particular burden because every device, switch, host, and router must process and possibly act on such traffic. In extreme cases, broadcast storms can occur where the quantity of broadcast traffic reaches a level that effectively brings down part or all of a network. For example, poor implementations of loop detection and prevention or misconfiguration errors can create conditions that lead to broadcast storms as network conditions change. The conventional wisdom for addressing such problems, has been to say, don't do that. That is, split large L2 networks into separate smaller L2 networks, each operating as its own L3/IP subnet. Numerous data center networks have been designed with this principle. For example, each rack placed within its own L3 IP subnet. By doing so, the broadcast domain and address resolution is confined to one top-of-rack switch, which works well from a scaling perspective. Unfortunately, this conflicts in some ways with the current trend towards dynamic workload shifting in data centers and increased virtualization, as discussed below. Workload placement has become a challenging task within data centers. Ideally, it is desirable to be able to dynamically reassign workloads within a data center in order to optimize server utilization, add more servers in response to increased demand, etc. However, servers are often pre-configured to run with a given set of IP addresses. Placement of such servers is then subject to constraints of the IP addressing restrictions of the data center. For example, servers configured with addresses from a particular subnet could only be placed where they connect to the IP subnet corresponding to their IP addresses. If each TOR switch is acting as a gateway for its own subnet, a server can only be connected to one TOR switch. This gateway switch represents the L2/L3 boundary. A similar constraint occurs in virtualized environments, as discussed next. Server virtualization is fast becoming the norm in data centers. With server virtualization, each physical server supports multiple virtual machines, each running its own operating system, middleware, and applications. Virtualization is a key enabler of workload agility, for example, allowing any server to host any application on its own VM, and providing the flexibility of adding, shrinking, or moving VMs within the physical infrastructure. Server virtualization provides numerous benefits, including higher utilization, increased data security, reduced user downtime, and even significant power conservation, along with the promise of a more flexible and dynamic computing environment. The discussion below focuses on VM placement and migration. Keep in mind, however, that even in a non-virtualized environment, many of the same issues apply to individual workloads running on standalone machines. For example, when increasing the number of servers running a particular workload to meet demand, placement of those workloads may be constrained by IP subnet numbering considerations, as discussed earlier. The greatest flexibility in VM and workload management occurs when it is possible to place a VM or workload anywhere in the data center, regardless of what IP addresses the VM uses and how the physical network is laid out. In practice, movement of VMs within a data center is easiest when VM placement and movement do not conflict with the IP subnet boundaries of the data center's network, so that the VM's IP address need not be changed to reflect its actual point of attachment on the network from an L3/IP perspective. In contrast, if a VM moves to a new IP subnet, its address must change, and clients will need to be made aware of that change. From a VM management perspective, management is simplified if all servers are on a single large L2 network. And I remember that from earlier if you extend L3 down to your access layer, you're going to need to manage IP addressing more than you would if they were not all the way down to the access layer. With virtualization, and not only that, you can bring, depending on what machine you've got connected into your access layer, you can bring your L2, L3 boundary all the way down past your access layer onto the machines themselves. With virtualization, it is not uncommon to have a single physical server host 10 or more VMs, each having its own IP and media access control addresses. Consequently, the number of addresses per machine, hence per subnet, is increasing, even when the number of physical machines stays constant. Oh, and we're at the 1 hour mark, so I'll just finish up this section. In a few years, the numbers will likely be even higher. In the past, applications were static in the sense that they tended to stay in one physical place. An application installed on a physical machine would stay on that machine because the cost of moving an application elsewhere was generally high. Moreover, physical servers hosting applications would tend to be placed in such a way as to facilitate communication locality. That is, applications running on servers would be physically located near other servers hosting the applications they communicated with most heavily. The network traffic patterns in such environments could thus be optimized, in some cases keeping significant traffic local to one network segment. In these more static and carefully managed environments, it was possible to build networks that approached scaling limitations but did not actually cross the threshold. Today, with proliferation of VMs, traffic patterns are becoming more diverse and less predictable. In particular, there can easily be less locality of network traffic as VMs hosting applications are moved for such reasons as reducing overall power usage by consolidating VMs and powering off idle machines, or moving a VM to a physical server with more capacity or a lower load. In today's changing environments, it is becoming more difficult to engineer networks as traffic patterns continually shift as VMs move around. In summary, both the size and density of L2 networks are increasing. In addition, increasingly dynamic workloads and the increased usage of VMs are creating pressure for ever higher L2 networks. Today, there are already data centers with over 100,000 physical machines and many times that number of VMs. This number will only increase going forward. In addition, traffic patterns within a data center are also constantly changing. Ultimately, the issues described in this document might be observed at any scale depending on the particular design of the data center. Okay, so here's where we start getting into the meat and potatoes. So that'll be perfect for the next video. Thanks for watching and see you in the next one.